So more general cases. This is if this is a true model. Yeah, again, we don't know what is a true model. We omit the x3 here. Okay, but here the no general statement are possible, which means is we don't know beta 2 will be overestimated or underestimated. We know, only thing we know is that this beta 0, beta 1, and beta 2 are biased. But in general, we cannot tell is it overestimated or underestimated. We don't know. Very specific case, right? So here, this one, when we omit this ability, this beta 1 and beta 2 will be biased, but the direction of the omitted variable bias can be analyzed. We can tell this will be goes up or this will goes down and so on, only if this experience is uncorrelated with education and also ability too. Then, as you saw, beta 2 times like beta 3, right? This one will be 0, so this summation will be 0, and then the new beta 2 will be still the same as beta 2. So that's why everything is not uncorrelated, completely uncorrelated. Only then we can say it's not biased by the omitting variable. Variance of residual. This is what we saw is a homoscedasticity, right? So the variable variance is it's not affected by the x1, x2, x3. It will be constant variable. It has a variable, but it's not increasing or decreasing. Okay, so wage is affected by the education, experience, and then tenure and so on, but this variance of the residual will not change by the education, will not change by the experience, will not change by the tenure. Okay, the sampling variance of the OLS slope estimator is given by this one. This is the variance of the beta estimator of the slope will be SST, which is the sample variation in the variable x, and then 1 minus Rj. Here, this R is not our model's R. This Rj is the R square from a regression of xj. So this is like a xj equals right, x1 plus x2. Yeah, of course, without here we are not including xj. You just taking out 1x and then so more precisely we have to say the I equals not j to the n and gamma I xi. So without j we can do the regression, and then you got a R square, and this R square is this R square. So if the all the independent variable they are not correlated each other, then this R square will be very small, right? If this is a small, denominator will be big, then variance will goes down. So if the R is a small, which means it's a uncorrelated, among the independent variable, and R square will be small and the variance will be small. Error variance. Error variance is about this one, is a sigma. So actually this is from the model. right? So what I mean by model is that you choose, okay, I will use this factor, this factor, this factor. You decide like a 4 or 5 factor. Okay, I will use this 5 factor and then estimate my y. That model will have an error variance because we don't know, it will not be exactly the one. You will have some kind of error here, right? And this error variance will be by model. So if you decide the model, the error variance is decided. Sample variance is different. This is because of we sample. So the variance is because we sample. This sample variance can be reduced if you increase the sample size. Yeah, increasing the sample size, more precise estimator. Yeah, that's true. This is the same concept, trying to find out population mean. If you increase the sample size, your sample mean will have a smaller variance. It's the same thing. If you increase the sample size, your estimate of the all parameter, I mean the coefficients, that coefficients will have a smaller variance. However, that even though increasing the sample size, this error variance will not decrease. Here, the error variance does not decrease by the sample size because this variance is inherited by the model. This is the what model. Doesn't matter how many sample you have, model itself has a error, and that error variance. So this is the two different things. Okay. So linear relationship among the independent variables. So you find out the regression on this xj on other independent variable, and r square of this regression will be higher if they are correlated, right? xj can be explained by others, then r will be higher. The sampling variance of the slope estimator of xj will be higher when xj can be better explained by other dependent variable. Do you remember the highly correlated the example I use is of like y equals 15 plus 3x1 plus 4x2, but if x2 is just 3x1, then you can replace it and you can change the value. So you cannot trust under this is 3 and 4, right? So this will be like a 3x1 plus 12x2, right? And then this will be the 15 plus 15x1. So when we have x2, I don't know, this will be 3 and 4. Maybe it can be 12x1 plus 1x2 will be the same, right? Mathematically, these two calculations are exactly the same, if this is true. Therefore, I cannot trust this number, and this will be higher. That's why this 3 can be like a 3.6 or 4. It can be 5, right? This one or certain factor can be better explained by other independent variable, then your R square of regression will be higher, and then the sampling variance of the slope estimator will be higher. Of course, it can change a lot. Under the perfect multicollinearity, the variance of the slope estimator will be approached to infinity. So this how many different number we can have? In perfect case, you can have infinitely many, right? So it can be, if you consider here the coefficient can be the negative number, you can have like a 100x1, right? Minus, I don't, to make a thing is should be 85, this is not good example, but 85 divided by 3 x2, still this calculation will be the same. So what will be the variance of this coefficient? Infinity. if this case, if it's perfectly correlated. Okay, this is average score, and then expenditure for the teacher, and this is the expenditure for the instructional material. This is the expenditure of other expenditures, and so on. So this is all money, right? How much money we spend. Actually, the school has a lot of money. They will spend more money on for the teacher. They will spend more money on the material. They will spend more other expenditures. All right. So mostly these three spending will have a highly correlated. Now, then it will be hard to estimate the differential effect of the different expenditure. Then you cannot trust on these numbers because they have a highly correlated. This is because all expenditures are either high or low together. So if one is high, then most of them, all the expenditure will be high, and so on. Right? And then in case, as a result, the sampling variance of estimated effect will be large. So sampling variance can be pretty high. That's why you cannot trust the beta 1, beta 2, beta 3 here. So multi-collinearity problem, as you see, it's better to lump all the expenditure category together because the effect cannot be entangled. So maybe you can just put together it's just one expenditure number. Or we can just dropping some of them, leaving only one expenditure and then dropping all others. So you can reduce the multi-collinearity problem. The problem is because they are not perfectly correlated, so if you omit, then you may have a omitted variable bias. So how can I tell we have a multi-collinearity? Because the all variable, even though they are not related to each other, but they will have a little bit of the correlation, right? So what you can tell is you calculated this VIF is a variance inflation factor, calculating this way, and then if this number is greater than 10, then we say there is some problem. Maybe because the multi-collinearity is too high, then your model has a problem. If this is a less than 10, then you can say, yeah, of course this 10 is kind of rule of thumb. There's no theoretical reason why it have to be 10 is the critical point. This is just like a 5% in the hypothesis test. Doesn't it have to be 5%? Why not 6%? That's kind of the people agree to use. Yeah, let's use 5% in hypothesis testing. So same way, this is kind of rule of thumb. If this is greater than 10, then yeah, we say there is a problem, and then if it's less than 10, then we say, yeah, we have a little bit of the collinearity, but it's fine. Misspecify the model. This is when we omit the one of the important factor, then we know all other. Here we just taking out this one out, and then all other coefficients will be biased. I know taking out will create a bias, right? However, this may reduce our the variance.